We are in section 3.9 continued. There's a note up here at the top that we should go ahead and give a star to. It says, remember that rates of changes are just derivatives. And then there's a box second on the page that talks about strategies for solving related rate problems. So the first thing is read the problem carefully. I suggest reading it twice. So try to read the next example before we go through it. So pause the video and think about it before we actually talk about it together. Second thing is draw a diagram or picture if one isn't provided. Some of the problems do provide pictures, but a lot of them do not. Third thing says assign variables to all the quantities that are unknown. And label all constants in the picture. Write the givens and the wants in mathematical notation. Again, this is where that implicit differentiation comes into handy. So there will likely be rates of the form dh, dt, dv, dt, dr, dt, dy, dt, d theta, dt, etc. at a particular moment in time, and or constants like x, r, or h. Next thing is write a general primary equation that relates the constraints and the constants to our variables in the problem. Here you will likely be using geometry or trigonometry. So the one that we did first in the last video was a geometric problem with a spherical balloon. And we will see both of these in the problems. The next thing says if any quantity in the equation is constant, you may replace it with the variable. If the quantity in the equation changes throughout the problem, it has to be left as a variable. And again, we're going to end up using similar triangles and different things along those lines. So a lot of stuff from previous classes. The next one, 7, says use the chain rule and implicit differentiation to differentiate both sides of the equation with respect to time. It's always with respect to time. Number 8 says substitute in the given data and solve for the unknown quantity or rate desired. 9 says include the appropriate units. So don't forget your appropriate units and make sure that your answer makes sense. So there's another example here that we're going to look at. This time it says the radius of a circular cone of fixed height, 30 centimeters, that means it's not changing, is increasing at a rate of 3 centimeters per second. How fast is the volume increasing when the radius is 8 centimeters? So, first thing is we have a circular cone. So you can imagine like a snow cone. And it talks about it has an increasing rate. So that would be our radius. The radius is increasing at a rate of 3 centimeters per second. It wants us to find how fast the volume is increasing when the radius is 8 centimeters. The other thing that's in here that I did not underline is that there's a fixed height of 30 centimeters. Fixed means that that's not changing. So if we were to go ahead and look at our cone, we have our radius and our height that I will go ahead and label. So here's our radius and the height. So we need to have a formula that's going to talk about volume and include the radius and the height of a cone. So go ahead and write that down. If you don't know the formulas from geometry, make sure that you look them up as you're going through the homework. On an exam, they'll be provided for you. So 1/3 pi r squared h is our formula that we have. And since the height is fixed, I can just substitute that value in. H is equal to 30. That's a fixed value. It's not changing. So our volume formula now becomes 1/3 pi r squared times 30, which just simplifies to 1/3 times 30 would be 10 pi r squared. And again, this only works when something is fixed. It's not changing. So it wants us to find how fast the volume is increasing when the radius is 8 centimeters. And we also know that the radius is increasing at a rate of 3 centimeters per second. So we know that dr dt is equal to 3 centimeters per second. And so from here we need to find how fast the volume is increasing. So that's going to be find dv dt when the radius is 8 centimeters. So right now we have our equation set up. We plugged everything in. Once we get this way, we're going to go ahead and use implicit differentiation and take a derivative of our equation with respect to time. So taking the derivative of v with respect to time is just going to be dv dt equals 10 pi r squared, taking the derivative of the right side with respect to time, is going to become 20 pi r times dr dt. From here, we know that we have some variables that we can sub in. We know that dv dt is what we're looking for. We know dr dt is equal to 3 and r is equal to 8. So going ahead and substituting those in, we have 20 pi r and our r value is 8. And then dr dt is 3. So we get that dv dt is equal to, if you multiply that out, it should be 480 pi. And volume is measured in centimeters cubed, and then seconds for our time.